Ok. Tá funcionando? Ok. Well, welcome everybody. Just a small information. We will have really our welcome address on Wednesday at 5 o'clock, when there will be a reception with the people from administrative staff of this school and of the Minister of Science. And later we will have a marvelous Italian cantatrice, which will give to us beautiful Italian songs, and we will have our friend and colleague Ugo Moschella at this or another piano. Not this, okay. So let us go directly to the start, and I will ask Professor Brandenberger to start with this lecture. Thank you.
Great. So can you hear me? So first of all, I would like to thank Mario and the other organizers for inviting me here. It's always a great pleasure to come to Brazil. And my lectures are going to be mostly on the blackboard, except for the first half of this lecture. And you will see why. So this is the outline of my lectures. I will first of all give an extended overview. Then I will talk about the main framework of early universe cosmology, which is the theory of cosmological perturbations. Then I will talk about early universe models. And I want to emphasize the word model. I'm not writing early universe theories, but I'm writing early universe models, because these are models and not yet theories. And for those of you who are graduate students, the challenge for you is to turn the models into theories. And so what I will try to emphasize throughout the lectures is the essential ingredients which your future theories have to obey in order to be consistent with the data. And data is something that I will focus on in the overview. Now, I must confess that I am partial in favor of superstring theory. And so the last topic that I will cover in these lectures is attempts to combine superstring theory with cosmology. And there have been some recent developments in this area just in the last month, and I will allude to them as I go on. So this is the menu for my lecture series, and I want to start with the overview. So, overview. So, cosmology has now become an observational science. When I started working in the field of cosmology, theory was way ahead. There were hardly any observations. But now it's completely different. Now there are a huge number of observations. Most of the observations are still consistent with our models. However, the models leave key questions unanswered, and this is a challenge for theory. So, but I want to impress you with the vast amount of observational data that we have. So we have several windows. We have the well-known optical window. So astronomers have been looking at the sky through optical telescopes for a long time. There's a CMB window, cosmic microwave background window, which I think all of you are familiar with. And then there's a new window, which is going to be very promising, which is a 21-centimeter window. And one of the few countries where research is being done in this window is actually Brazil. And then there's the gravitational wave window. So let's start with some nice pictures. So in experimental physics, observational astronomy, we have instruments. And in astronomy, these instruments are located in beautiful places on the surface of the Earth, like here in South America, the Andes, an optical telescope. And with the optical telescope, we look at the sky through the optical window, and we see galaxies. But for cosmology, for early universe cosmology, galaxies are much too small. We have to look beyond galaxies. So we will replace each galaxy by a point, and we will look beyond, we will look at the distribution of galaxies. So this is a projection of the sky onto a plane, like the projection of the surface of the Earth, and each point corresponds to a galaxy. And what you should take away from this plot is that that there are many galaxies, and that galaxies are not randomly distributed, they are not uniformly distributed, there is structure in the distribution of galaxies. So this is a two-dimensional map. There's missing information, and this missing information is a distance. But by measuring the redshift, we can fill in this missing information. And if we project one angle in the sky, and we plot distance versus the one remaining angle in the sky, then we have this distribution of galaxies. So again, each point is a galaxy. And far away from us, we see only, so we are in the center. Far away from us, we see only the very bright galaxies. Therefore, there seem to be less galaxies if we go further away. This is just an artifact of the fact that we only see bright galaxies far away. Again, galaxies are not randomly distributed, and they are not uniformly distributed, and you can quantify this data. So we now have three-dimensional information about the distribution of galaxies. We can expand, we can do a Fourier expansion, and and then we can plot the power spectrum, the amount of structure, as a function of wave number. So small wavelength, large wavelength, and a solid line is the data. So we have quantified data. And I do want to go back one slide because I want to impress you with how fast the field is evolving. So now we have maps, redshift maps of millions of galaxies, whereas when I started in the field, we had information about 1,000 galaxies. So we are probing deeper and fainter. So this is the current status. Now, there are many new telescopes which are in development. These are optical telescopes or infrared telescopes. And I'll just give you a couple of examples. The LSST, Large-Scale Synoptic Telescope. There are telescopes that will fly in outer space, like the Euclid satellite. And then there are specifically constructed infrared satellites, like the James Webb Telescope, which will be launched soon. So with these, we will explore, okay, maybe not so soon. I'm a pencil and paper theorist. I'm not part of collaborations, but it will be launched. And you see, within 5 years, probably. Okay. You see, it's not so urgent. We have lots of theory to develop. Data is ahead of us now, and we shouldn't let data be too much ahead of us. Okay. So, now another window is the microwave background. This is a microwave background telescope, the ACT, Atacama Cosmology Telescope, also located in South America, in the Andes. Then there are telescopes located in even more fascinating places, like on the South Pole. This is a South Pole telescope, which McGill is involved in. And there are also telescopes which have flown in outer space. And so these telescopes probe the intensity of the microwave background in different directions in the sky. And with these complicated telescopes, expensive telescopes, not expensive by particle physics standards, but expensive, you get this beautiful map of the distribution of temperatures across the sky. Different colors indicate different temperatures. You see, different colors indicate different temperatures. So, and again, this is a projection of the sky onto a plane, and you see that to quite good accuracy, the temperature of the microwave background is isotropic. Why? Now, if we probe to 1 part or to 3 parts in 10 to the 5, we see the anisotropies emerging. So I'm sure you've all seen this map. It's from the WMAP satellite. So different colors means different temperatures. And again, this is 3 parts in 10 to the mine in 10 to the 5 of the background. So now we have this beautiful data. The temperature is not isotropic. It is not randomly distributed. There's structure. And the way we quantify these structures, we expand this map in spherical harmonics, and we plot the power in each spherical harmonic. Okay, so this is a power amount of anisotropies. This is the angular scales, small angular scales, large angular scales. And the black dots are the data with some statistical uncertainties and some systematic uncertainties here. And now the red curve is an artist's curve which fits the data fairly well. And the artist was told to take this data and given 6 free parameters to match the data. And I will tell you who the artists were when we go on. Just for those of you who are interested in this puzzle, the artist did this theory in 1969, 1970, which is 10 years before inflation. Okay, so now if we look at one point in the sky and we measure the spectrum of the microwave background at that point in the sky, so intensity as a function of wave number, then this is the data that we have. So this is the frequency intensity distribution at one point in the sky. This is observational data. The error bars are smaller than the thickness of this curve. And this is the black body curve of about 3 degrees Kelvin. With this slide, with this data, cosmology has become a high precision observational science. Not all data in cosmology has this precision yet, but we have lots of data, and there are error bars, and the error bars are rapidly getting smaller. So this is part 1 of the data. Okay. So now I will switch briefly to the board. So we have to have a framework to interpret this data, and keep down. Okay, good. Framework. The framework consists of a theory of space and time, in which matter lives. And space and time is described by Einstein's theory of general relativity. And for now, we will take matter to be described by classical perfect fluids. Good. Okay. So if we take this framework, we see that the universe is, to first approximation, homogeneous and isotropic. So we can write the metric in this form. We also see no spatial curvature, so I'll neglect the spatial curvature. This is just Euclidean three-dimensional space, scale factor, physical time, co-moving coordinates. This indicates the size of space. And if you take A dot over A, this is defined as the Hubble expansion parameter. Okay, so this is the way we describe homogeneous and isotropic space-time. And then the way we describe matter is in terms of fluids. Fluids are described by an energy density. There are different fluids. Fluid number I has energy density rho sub I, and it has some pressure. And the equation of state is P sub I divided by rho sub I. And continuity equation says that this is the way that the energy density in the different fluids evolves. And the Einstein equations tell us that This is the sum of the energy densities. This is the constant that indicates spatial curvature. And I have to check if I got the sign right. Yeah, I think, according to my notes, this is right. Okay, so these are the basic equations that I'm going to use for now. Okay. So, if we use this framework, then we can plot as a function of time. We can plot various energy densities. And I will call the current time, the present time, t sub 0. And at the present time, we see the universe being dominated by matter, cold matter, which is pressureless. This is today the dominant contribution. But there's also radiation, which is a microwave background. It has W equals 1/3. And so if you plug this into here, you see that if you go backwards in time, the energy density in radiation increases faster than the energy density in matter. And so, although today radiation is subdominant, if you go back in time, there'll be a time when they cross. So this is rho sub r, this is rho sub m, and this is called the time of equal matter and radiation. Okay. Now, if we actually use the temperature of the microwave background, and we measure the energy density in matter today from the matter distribution, then we know this ratio, and then we find that this transition happens before the recombination. So as we go back in time, the universe heats up. Eventually, hydrogen atoms become unstable. This is the time of recombination. And before recombination, the universe is a plasma. And after recombination, the universe is electromagnetically neutral. Okay. And then we have something else. We have spatial curvature, which is this term here. So in my list, we have rho sub k. This is the energy density in spatial curvature. And this corresponds to W equals minus 1/3. And so the energy density of that grows very slowly compared to the other things. So this is rho sub k. And then I'm missing one thing which appears to dominate today, and this is rho sub lambda, which corresponds to W equals minus 1. This is the cosmological constant. I don't have another color, so this will be red again, and it will be red because it's danger. This red indicates danger. So today we seem to see that this cosmological constant slightly dominates rho sub lambda. Okay? However, this term is inconsistent with superstring theory. So this one does not exist. See, I do want to make some controversial statements even in the first lecture. So we have to revise what we know now. Okay, let's look at this curve. Why should the spatial curvature be so small today? Because
why is not the other way around?
Why is it what?
The other way around. Because this term is there, superstring does not exist.
We can argue about, see, I like superstring theory, and we will have a seminar on Friday which is devoted to the intrinsic instability of de Sitter space, which you see completely without string theory. This is Leila who will be giving this talk. So I think, so the question whether de Sitter space is stable or not is a question which has been worked on for a while, and there's increasing interest in that. And now I'm partial to this, so so what I said until now is fact. What I'm saying now is opinion. I think consensus is growing that de Sitter space is unstable. Polyakov, Wood and Samus, Verlinde, provided he corrects his sign error in his November 2016 paper, all indicates that de Sitter space is unstable. So there are more reasons than superstring theory to question this. But we can talk about that. That's not the subject of that. Okay, so I've shown you data, and I'm going to go back to data now. Can we maybe lower the screen completely? So you see, based on this picture, on current data plus theory, we find that the universe was hot, was a plasma, and then we find that there was an early time before which the universe was an electromagnetic plasma. Afterwards, it's neutral, and this is when the microwave background was produced. It's a long time until the microwave background has been observed, and the fact that the microwave background is almost isotropic means that there could have been no inhomogeneities of large amplitude at early times. So all of the galaxies have to have formed at late times. So now, if you go back to here, if we probe further back into the past, you see that the temperature of the microwave background increases, and eventually you have a QCD plasma, and eventually you have a plasma of other particle interactions. So this period here is rich of particle physics, and this is illustrated in this graph. So again, this is time. Whoops. So the vertical axis is time, and you see the various phases. So this, we are at the top, and the microwave background is recombination, and there are many other phase transitions that happened earlier, and we can, in principle, probe all of this by looking at the observations carefully. So there are new windows, and one of the new windows is the polarization of the microwave background. So the microwave background has two polarization modes, E mode polarization, B mode polarization, and we have already measured, we already have polarization maps. This is a Planck polarization map of the microwave background. So in this map, you see both amplitude of polarization and very faintly you see a polarization axis. Very faintly. But what you see here is so far only E mode polarization. So if you analyze, if you expand this map in spherical harmonics, and you look at the E mode polarization, the power spectrum of E mode polarization, you have this data. And here you see, here when the red curve is subtracted, you see the remnants with error bars. So this is the known E mode polarization of the microwave background. This is the cross correlation between E mode and temperature. So again, we have a theoretical curve in red, and we have the data in blue, and the error bars are in the bottom. And so far, we have not measured the B mode polarization. And there are new telescopes which are going after the B mode polarization. For example, there's the Simons array, which is also in the Chilean Andes. Good. So this is the new aspect of the microwave background window. So now the next window that I'll mention is a 21 centimeter window. So if we have time, this is a microwave background. We have photons traveling to us. Now, if there happens to be a cold cloud of hydrogen, hydrogen dominates matter before reionization, before galaxies start to form. If this photon ray passes through a cold cloud, this one does not, then the photons will excite the 21 centimeter line of neutral hydrogen. And so therefore, if we look at the microwave photons in a frequency which corresponds to 21 centimeter, or redshift at 21 centimeter, we will see an absorption feature compared to where there are no gas clouds. So the 21 centimeter window is a new window which allows us to probe the distribution of baryonic matter, which is predominantly neutral hydrogen, before the epoch of star formation. So this is a new window, and we will learn something about the distribution of matter between recombination and star formation. We will also learn other things when we probe the 21 centimeters at low redshift, this window. So it's a new, very promising window. And the first telescope, which is online, which is starting to take data, is the CHIME telescope. So this is a telescope which plans to measure 21 centimeter radiation at fairly low redshift, so probing epochs redshift lower than 2. There's another telescope which is in construction in South Africa, HIRAX. They're very different technology. This is an array of dish telescopes, not cylindrical telescopes, that has the same goals as CHIME. And then there's a Brazilian proposal, the project, which is funded, BINGO, which I think was initially supposed to be located in Uruguay. It might now be located actually in Brazil. It's a collaboration between England, Brazil, Uruguay, and also a small contribution of Switzerland. It has, again, the same goal. So we will explore the data in this new window. And this is the future of 21 centimeter. It's a square kilometer array, which will be half South Africa, half Australia, an array of such dishes, which will be in the deserts in Western Australia and in South Africa. And with this SKA, we will actually be able to map out 21 centimeter here. So, finally, we have the gravitational wave window, which has just opened up, thanks to the observations from LIGO, and this is one of the LIGO sites. And this is the famous event, the signature of coalescing black holes, seen from both LIGO observatories. And the future is bright, because LISA is now funded, and that's going to increase the sensitivity to gravitational waves. It's going to allow us to detect gravitational waves at large length scales. And these are the sensitivity forecasts for the spectrum of gravitational waves produced in the early universe. So we have small wavelengths, intermediate wavelengths, large wavelengths. So small wavelengths probed by LIGO, larger wavelengths probed by LISA, and even larger wavelengths, cosmological wavelengths probed by pulsar timing arrays. Okay, so we have lots of data. And to conclude the slideshow, cosmology it always had the first goal, namely to understand the origin and earlier evolution of the universe. That has been the goal of cosmology for millennia. But now that we have data, we have a second goal, and this is to explain the observed large-scale structure. And finally, since we have so much data coming up, the third goal is to make predictions for future observations. And since the early universe was dominated by fundamental physics processes, we should look for signatures of these fundamental physics processes in all of these observation windows. So one thing that I want to emphasize here is that essentially all of the data that I've showed has to do with inhomogeneities and anisotropies, with structure, not with the background cosmology. So now we are in an era where cosmologists have to consider not just the backgrounds, but the fluctuations. And as I will go on, I will show many background cosmologies which seem perfectly fine, just at the level of background cosmology, but as soon as you put in perturbations, things go disastrously wrong. So we have lots of data, and hopefully we will learn lots about fundamental physics from it. So at this point, can you maybe, I won't need the slides anymore. So what is here on the board, this is standard Big Bang cosmology. That is expressed by everything that's here. But standard Big Bang cosmology cannot explain any of the data that's related to inhomogeneities. So let me illustrate this. Problems of the standard Big Bang. So I'll start with the first problem, which is to explain the isotropy of the microwave background. So this is time, this is space, co-moving coordinates, and this is the time when the microwave background is released. And we are looking back at the photons which travel from last scattering to the present time. And according to standard Big Bang cosmology, there was a Big Bang. And now we can calculate what fraction of this region of space, where we see the same temperature, could have been causally connected if this standard Big Bang timeline is correct. So we can calculate the forward light cone, LF of t, forward light cone. This is the maximal area of causal contact. And an easy exercise is to show that this distance here corresponds on the sky to about 1 degree. So as a consequence, there is no way in standard Big Bang cosmology to explain the isotropy of the microwave background. This is the horizon problem. So, what about structure formation? So here I will draw again a space-time diagram. X, and here I will plot equal matter and radiation. Now, are there graduate students here? Who's a graduate student? I know that, okay. Good, so now I'm going to give you a homework exercise. And a homework exercise which is impossible to solve by looking at your iPhone and looking at the textbook on cosmology. Because in those textbooks on cosmology, they will say exactly what I'm going to say, but I am lying. I am sweeping in two assumptions, hidden assumptions which I'm not going to tell you, and you have to find these two hidden assumptions. Now, a bonus problem is to try to try to avoid the conclusion that I'm going to reach by making use of the two hidden assumptions that I'm sneaking in. I know very well that I'm sneaking in two hidden assumptions, but I don't know how to make a cosmology that works by fixing these. Okay, so be careful. I'm sneaking in two hidden assumptions. So again, this is time, and this is the Big Bang. This is equal matter and radiation. This is the region of causal contact, the horizon. Nothing can travel faster than the speed of light, so no causal process can produce inhomogeneities on length scales larger than the horizon. No causal process can produce fluctuations on scales larger than the horizon. Okay. Good. So today we are observing the microwave background, and we are observing large-scale structure, and we see non-trivial fluctuations, non-random fluctuations on scales which are quite close to the present horizon. Now the horizon grows as t, whereas the physical length of fluctuations, lambda physical of t, grows as the scale factor, which at late times grows as t to the 2/3. Okay? So structures on large scales are larger than the horizon at equal matter and radiation. Okay. So since the only force that is acting on large distances can be gravity, and gravity is a weak force, therefore, if we see non-trivial fluctuations today on this length scale, there had to have been non-trivial fluctuations on the corresponding length scale at this time. Now, this length scale is larger than the horizon at the time, and therefore it is impossible to have a causal theory of structural formation in standard Big Bang cosmology. Now, the reason I'm fixing the time of equal matter and radiation and not some other time is that gravity allows structures to start to grow at the time of equal matter and radiation. So that's a good reason of picking this time. This is a structural formation problem. So we can't explain the isotropy of the microwave background in standard Big Bang cosmology, and we can't explain any of the structure that we observe today on large scales in standard Big Bang cosmology. There's also the flatness problem. So we don't see spatial curvature today, but since spatial curvature decreases very slowly compared to energy density and other stuff, spatial curvature at early times had to be tuned to an extremely small value in order to be invisible today. That's the flatness problem. I'm not going to talk about the flatness problem much. And finally, standard Big Bang cosmology predicts that the temperature was infinite, which makes absolutely no physical sense. Singularity problem. So you have the horizon problem, structural formation problem, and the singularity problem. Okay. Good. So now I want to work out the criteria which one needs to have a successful model of the early universe which can solve the horizon problem and the structure formation problem. And the first thing I have to emphasize is the difference between Hubble radius versus horizon. So they are in general different. And most cosmologists use the word horizon when they mean the Hubble radius, which is very confusing, but they're different. So the horizon is the thing which I drew here, which is the forward light cone of some initial point. You have a Cauchy problem. You decide the initial time when you want to oppose initial conditions, close to here. Then you draw the forward light cone, and that's the horizon. So the horizon carries causality information. Causality information is associated with the horizon. Now the Hubble radius is defined as H inverse of T. Inverse Hubble expansion rate. This is a completely local concept. It doesn't carry any causality information, but it is relevant for fluctuations. It turns out that if you have wavelength greater than H inverse of T, then fluctuations are frozen. Whereas lambda smaller than H inverse of T, fluctuations oscillate. Okay, so this I will ask you to accept now. In the second part, where I talk about the theory of cosmological perturbations, you will see this emerging. So, if you want to create fluctuations using causal physics, you have to move things around. You can't do that in the phase where fluctuations are frozen. So a fluctuation mechanism has to work on scales smaller than the Hubble radius. Okay. So now I want to give you 3 examples of cosmologies where the Hubble radius is different from the horizon. And these will also be 3 paradigms for structure formation. So I'll give you example 1. And what I'll plot is scale factor as a function of time. By the way, those in the back, if I start to write too small, please raise your hand. So in this first scenario, I'm going to assume that the scale factor is constant until some time, which I call T sub I. And then afterwards, it starts increasing, like in standard Big Bang cosmology. This is standard Big Bang cosmology like. This is an emergent phase. Okay. So now let's see what happens to the Hubble radius and to the horizon in this context. So here will be time, and here will be various length scales. And this will be this T sub I. So time runs from minus infinity to plus infinity. And so the horizon is the forward light cone of some initial point at t equals minus infinity. So the horizon is infinite. There's no limit to causal contact because t goes to minus infinity. Now, what does the Hubble radius do? Well, the Hubble radius increases linearly, like in standard Big Bang cosmology. And the Hubble radius is infinite in this phase because the scale factor is constant. Scale factor constant, h equals 0, h inverse infinity. So the Hubble radius does this. This is what the Hubble radius does. So, you see, Hubble radius is much smaller than the horizon. So that's my first example. My second example is one that several people here will like a lot. It is a bouncing cosmology. So here, the scale factor is a function of time. Oops. This is standard Big Bang cosmology like. This is the inverse of it. So you have a contracted universe from minus infinity to 0. You have some new physics that gives us a non-singular bounce, and then a transition to standard Big Bang expansion. Okay, so what happens to space-time sketch? So the Hubble radius is the same as in standard Big Bang cosmology. It is inverse in the contracting phase. Exactly at t equals 0, h is 0, so it's infinite, so it has this shape. This is the Hubble radius. The horizon is infinite in both cases. And so you see the Hubble radius is much, much smaller than the horizon. No. No. No, this is not standard Big Bang like until here.
Yeah. Then before that, what was that?
Something which is not standard. And something which I will return to in my last lecture. I'll give you a concrete example of that. This is in the class of emergent cosmologies. Okay. Now you see, my third example is the example which most people give as the only example. So the third example is where you assume that there is a phase where the universe expands exponentially. Phase of exponential expansion between a time ti and tr. So now the space-time diagram looks like this. You have tr, ti, and you have 0. We are way up here. So the Hubble radius is like in standard Big Bang cosmology. Exponential expansion means Hubble h equals constant Hubble radius. And in this pre-inflationary period, you have something which inflation does not describe, but let's assume the most conservative assumption, something which is dominated by regular matter, then we have this. This is what the Hubble radius does. What does the horizon do? In this phase, the horizon expands exponentially because space expands exponentially. This is the horizon. Okay. So these are three paradigms where you can ensure that the horizon becomes much larger, exponentially larger than the Hubble radius. And now in all of these three scenarios, you have solved the horizon problem, because the horizon is infinite here, the horizon is infinite here. If this phase is long enough, the horizon is sufficiently large. And in all of these three scenarios, if you trace back the wavelength of cosmological perturbations, they emerge on sub-Hubble scales. So you can imagine a causal structure formation mechanism working because lambda is smaller than the Hubble radius here too. And here too, provided that this phase of exponential expansion is long enough. Yes, you can ask this question, but I'm not going to answer it yet because I'm going to tell you about the problems that each one of those faces. That will be lecture 3. Okay. But sure, in private, I can tell you much earlier than that. Finance, yeah. Good. Okay. So now comes my list of criteria which a successful model of structural formation has to satisfy. Criterion number 1 is H inverse of T, much, much smaller than the horizon today. That's lambda. The wavelength of cosmological fluctuations emerges sub-Hubble. So these are the two criteria which I explained here. Third criterion is you need to have super Hubble evolution. And the fourth criterion is that you need to have mechanism producing scale invariant fluctuations. So same amplitude fluctuations on all length scales, because that's what observations of galaxy distribution of the microwave background indicate. So these are the 4 criteria. Okay, good. So now I have 3 minutes. So these are criteria. So any one of you who wants to construct a new model of the early universe, this new model of the early universe will have to satisfy these 4 criteria. So now I want to end with 2 graphs. Why do I need this? So I want to have, good. So I told you that the artist who first discussed the agreement between observations and early universe theories, these artists were Peebles and Yu, and Zunyaev and Zeldovich. And I'm going to give you the Zunyaev-Zeldovich argument. (1969). They have a beautiful paper in which there's the following graph. This is time. This is co-moving coordinates. And in this graph, you have the time of recombination, and you have a curve which they call the Jeans length. And this is the length scale above which fluctuations are frozen, below which fluctuations oscillate. sub-genes, fluctuations oscillate. The gene's length will be the Hubble length, above which they are frozen. So, co-moving scales. Now, different wavelengths. Okay. So, the fluctuations of, so Zurняев and Zeldovich assumed that there is some mechanism which produces super Hubble fluctuations in the early universe. And then they realized that as a function of wave number, the scales will have done a different number of oscillations between when they start to oscillate and when the microwave background is produced. This one has done 0 oscillations, this one has done a quarter, this one has done half an oscillation. Now comes the second and last picture. If I have time, this is my surface of constant temperature. This is space. Okay. So now if you look at the length scale, where you catch a wave at maximal amplitude, then since the photons are released with the same temperature, same frequency, they will have different frequencies when they arrive. So this wave you catch as a standing wave, maximal amplitude. It will be a maximum of the temperature fluctuations. If you catch a wave when it's maximal velocity 0 amplitude, when it's a quarter or 3/4 of an oscillation, this photon will arrive at the same temperature as this photon. So minimum of the temperature anisotropies. This one has done half an oscillation, you catch it at a maximum. So Zurняев and Zeldovich have this picture, and then they predicted that if you look at the temperature fluctuations as a function of angular number, then you will get a peak corresponding to this. You get a trough corresponding to this. You get a peak corresponding to this, so on. And if you have scale invariance, you'll have a plateau here. So these are the acoustic oscillations in CMB. They are produced by this mechanism. They were predicted in 1969, 1970 by Zeldovich, Zurняев, Peebles, and Yu. And this is what was found in the late 90s by satellites like Boomerang and later WMAP. So the successful agreement between the microwave anisotropy spectrum and theory, it assumes these ingredients. So any theory that you construct that satisfies these 3 criteria will produce for you the same kind of agreement with observations that the inflationary model gave us. So, the end of this lecture is that using the data about fluctuations, you can probe the early universe, and the data gives us the guidelines on how to construct a good inflationary model, a good model of the early universe. And the second lecture, I will talk about the theory of cosmological perturbations. So you see there were no equations today, almost no equations. I'll make up for that tomorrow. So thank you.
I don't know whether it is the right time for my questions, but anyway, if it's not, you can tell. The detection of B mode would definitely confirm inflation. Another question is, how does...
Let me address this one first. All of these models that have these criteria will produce the same thing for the B mode. So you will hear everyone saying that B mode, smoking gun of inflation. Absolutely false. It was always false. It will always be false. If you want the details, I have a paper with the title, Is B-mode polarization the smoking gun of inflation? Question mark. And if you see a paper like that, a title like that, you will know that the answer is no.
Okay, you come in detail with this question, I believe, when you treat the models.
Yeah.
Are you planning to come back to this question? B model and models of the early universe.
Okay. I'll come back in the next lecture.
Yeah,
At the end of the next lecture, I will discuss gravitational wave production, and you will see that these models produce the same features for gravitational waves.
Okay. My other question is related to gravitational waves. How do you see that we can use it in the not so long time near future to clarify the early or define the early universe model?
Right. So again, I will get to that at the end of next lecture, but the different models will produce slightly different amplitudes of gravitational waves. And in fact, bounce in cosmology, one of the problems is that they typically produce too much. So that's one thing. Then there are also many other processes that can produce gravitational waves. So there are many ways in which we can learn about the early universe using gravitational waves.
Let's finish now. Thank you. We have a break of 10 minutes, and then we come back. Okay?
And graduate students, you should remember that you have a homework problem to solve.
Oi, Ana, oi, Louro. O Video Show voltando cheio de novidades. E uma dessas novidades é que esse trio poderosíssimo vai estar junto para apresentar para vocês. De segunda a sexta, sempre ao vivo, depois do Jornal Hoje.
The horizon we are talking about. No, yes, not.
Além disso, 2 novos